President of DePal Consulting Limited, and DePal specializes in working with generation and load customers, getting optimally connected to the grid and the associated regulatory intervention work. Today we have an exciting presentation on how to optimize the grid. And we know that in Alberta in the past several years, we've expanded the grid, and now the focus needs to be on optimizing the best use of the grid from what we have. And these presentations deal with this exciting topic. First, before we get started, I'll just help you navigate the control panel. You can see an orange arrow, and that lets you close or open the control panel. Just so you know, the presentation is being recorded, and you will be emailed a soft copy of the presentation once we're done. There is a question, a way you can ask questions through text, and please do that as the presentation goes on. And at the end of the session, we're going to answer all the questions. Plus, at the end of the session, you'll be able to raise your hand and ask the questions verbally. We'll take you off of mute. Everybody's muted now except for the presenters. And we'll take you off mute at that time. You'll be able to ask your questions, and the panelists will be happy to answer. And now I just want to introduce the panelists. So first of all, in the first box there, you've got Brendan Kelly. And Brendan is the Canadian General Manager for Smart Wires. He's based out of Vancouver, BC. Brendan took over the role 6 months ago, having led the Smart Wires European business expansion for the past 3 years. Prior to that, Brendan held a number of roles in planning and operations with the Irish transmission system operator EirGrid. Most notably, he was responsible for the connection design of over 2 gigawatts of wind generators to the Irish system, something that Alberta is going to be going through in the next few years. Brendan is an active member of CIGA and IEEE and has authored several technical papers on topics of power system planning and power quality. Next is Marc Brunet-Watson. Marc joined BBA in 2019 as the Director of Power Systems and Analysis, and that was to grow and expand the network planning and system study service offering. With 20+ years of experience in Canada, US, and Australia, and broad knowledge in power system engineering, both in the public and private energy sectors, Marc's technical expertise ranges from transmission network and planning to infrastructure investment analysis and project sponsorship. Marc is highly valued for his understanding of transmission plan development and implementation in a regulated operating environment, and for his detailed knowledge of the technical and financial operation of the energy markets. And Marc and I got acquainted yesterday, and I think he's going to add a lot of value in his conversation today. Marc is a true disruptor who is obsessed with finding better, more efficient ways to get things done, and he has a proven track record of delivering projects that require complex integration of systems, identification of capability shortfalls, and working with others to come up with innovative solutions that provide a pathway to success. So Brendan is going to give his presentation first, followed by Marc, and then we'll have the Q&A at the end. So take it away, Brendan.
Okay, thank you, Ed. I'm just going to try to share my screen here. There we go. Okay, perfect. Okay, so thanks very much, Ed. Thanks for the introduction, and welcome along, everybody. Good morning or good afternoon, wherever you're joining from. I'm going to be talking today about power flow controllers and how they can be applied in the transmission, the distribution context, and specifically we'll focus on advances in power flow controllers and more recent developments from kind of some of the well-known or well-established controllers that have been installed in the system for a number of years. So just to give you a quick overview of what I'll talk about. So we'll talk firstly about what power flow control options exist and how utilities are leveraging them across the system to optimize across the world to optimize the grid. We'll then move into kind of talk about what developments have been made and advancements have been made in recent years, how they're being applied at scale globally, and what's the impact for generation and demand customers, because power flow control as a solution can help generation demand customers as well, particularly on the interconnection side of things. So I guess just to set the scene, first of all, you know, it's a very uncertain electricity landscape right now, and has been for the last 5 to 10 or 15 years. We've had rapidly changing generation portfolio, shift away from oil and coal towards more renewables in the system, which come from different parts of the network than the network was traditionally designed for. On the load side, we can no longer rely on 2 or 3% load growth per annum, and it's becoming harder to predict what the load's looking like 18 months out, let alone 20 years out to justify investments. And then added to that, there's additional capital pressures on utilities to lower costs, lower rates, and lower costs and lower prices really drive economic growth in different provinces and regions. So a tough time for utilities, and power flow control is a solution a low cost solution that can help mitigate some of this uncertainty. So at the really 50,000 foot level, we've got a very simple electrical network scenario here, where we've got generation on the left hand side and load center on the right, and you're squeezing power through the network towards the load centers. In this case, if we lose, planning for N-1, we lose the bottom circuit here, we overload the top element or the top circuit by 5%. And you can see that the power is not distributed evenly across those 3 intact circuits, and in fact is utilized about 50% of the total overall capability of those circuits. Traditional solutions to this might be redispatching generation, reconductoring the constrained element on the top, or even building a new circuit between the generation and load center. And what power flow control really does is helps you to maximize the utilization or even out the power flows across those intact paths. So in one way, you can push power off constrained elements onto underutilized lines, or in another way, you can install a flow controller on a kind of a lightly loaded line and pull power down that. And in that way, you can move towards this theoretical 100% maximum utilization post contingency, with kind of optimized deployments across the network. Traditional solutions for this, you'll all be familiar with phase shifting transformers. They've been installed on, not just in Canada, but across the world for over 50 years at this stage. And really what they do is they can be installed in a circuit and change the phase angle between the sending end and the receiving end on a particular line. And they do this in the classic kind of power flow equation shown. They impact the sine delta aspect of that equation, and doing that you change the power flow. PSTs are used kind of across the world to maximize transfers between 2 different areas of the network and relieve bottlenecks. And you can see on the left hand side, there's a diagram here showing that when the PST is on center tap, so it's no phase angle across the PST at all. You've got an even distribution of power across the 2 circuits. But as you tap that or change the phase angle on the PST, you buck power or push power off it, or you can kind of go to a negative phase angle here and pull power onto the line that the PST is connected to. Now PSTs are, you can see physically what they look like here, but they're custom built devices for specific needs. So for example, if you need a PST to connect 2 areas with a 40-degree angle separation, on a 1000 MVA line, rated line, you buy and procure that PST for that specific application. So it makes them very custom built and used for very bespoke applications. Typically takes 2 to 3 years to manufacture and deliver PST at site and commission it. They're extremely good solution for connecting 2 areas with large geographic or electrical separation, basically areas with large angular separation. But from a kind of a physical standpoint, you install them, as you see here, connected to the substation bay, and they usually have a bypass protection bay as well to carry out maintenance and facilitate outages of the PST. From a control point of view, you would typically set a PST pre-contingency for a post-contingency event. So may not always be the most optimal application of a PST, and you don't want to be changing taps too often, as this can impact kind of the tap changers and impact kind of life cycle and maintenance costs for your PST. Other power flow control solutions that have been installed again for the last 50 or 60 years, series capacitors and series reactors. And Unlike the phase shifter, they actually impact the reactance of the line component of your power flow control equation. And in effect, what they do is they just inject a voltage at 90 degrees to the line current, which synthesizes a change in line reactance. So as a series capacitor will reduce your line reactance, the power flow control equation reduces the denominator and increases your power flow. And on the flip side, a series reactor will increase your denominator there, which will reduce your power flow on circuit. And again, just very simplified diagrams on the left showing when you install a series capacitor, you're drawing more power on a path, and a series reactor is pushing power, booking power onto the parallel circuit. So physically, again, what these look like, a series capacitor, both of them are insulated from ground, so they're installed at line potential or line voltage. And traditionally, series capacitors have been installed on, extra high voltage circuits. And in Canada, we see them quite often connecting kind of large hydro dams in the north with load centers in the south. And all that does is it just brings those two areas electrically much closer together. On the series reactor side of things, you can see much more compact. It's used typically for kind of power flow control, thermal power flow issues, usually in kind of dense urban centers, and it can also be used to reduce fault currents as well. So more recently then, we've seen sort of a move towards power electronic based power flow controllers, and specifically what we call static series synchronous compensation devices, and which form part of a unified power flow control installations. The first of these was installed in 1998 in American Electric Power in the US, and it was built by Westinghouse in the US. And effectively, it has the same electrical components electrical capabilities as a series capacitor or a series reactor, in that it impacts the reactance of the line. And it does this by injecting a voltage in series with the line at 90 degrees to the line current. So there's a number of these SSSCs and UPFCs installed around the world, in the US, in Spain, and in Southeast Asia as well. And I suppose the technology really developed as a result of cost reductions in IGBT power electronic devices. So these are what's used to create this voltage waveform that's injected in series with the line. And of course, IGBTs and voltage source converters are used in many other applications, including STATCOMs, HVDC systems, and even in wind turbine and solar installations as well. So one of the major advances then in the last kind of 7 or 8 years in this is a move towards more modular power flow control, modular solutions that fit kind of today's dynamic environment. And these are fact-based technologies, so taking that same SSSC core technology and reducing it down into a kind of a smaller package, so to speak. And these solutions, they kind of reduce the need for a transformer, they reduce the need for air cooling, a lot of the auxiliary cabling and communications cabling has been simplified, and just makes a very simple solution option for our utilities. And from a planning perspective, how this actually what this means, or how this can help, I suppose, is it's a scalable solution that can be, you can install a solution today to solve today's needs, and scale that up or down in time as more needs materialize on the grid. So it from that point of view, it really helps the utility minimize risk as they develop out the grid. These solutions, again, they're different from phase shifters or series capacitors in that they're off-the-shelf solutions. So the same device can be installed at 25 kV as can be installed at 500 kV, which means that it can be installed very, very quickly, moved around your grid very, very quickly, and also as they're off-the-shelf, they can be delivered very, very quickly. And kind of from a footprint point of view, I'm showing here the AEP SSSC installation that I talked about earlier on the bottom right, and the equivalent modular SSSC installation. So you can see vast improvements in terms of the footprint that's required, and also in terms of kind of just how it's installed and connected So the complexity around installation and operation has been vastly removed with the more modular solutions. So how do we use kind of modular power flow controllers to manage uncertainty? I've talked about this idea of being able to phase or scale these to meet grid needs in time. So I'm showing here a kind of MPV comparison of a traditional conventional series capacitor solution with a modular power flow control equivalent solution. And you can see that if you want to install a series capacitor or modular solution, the same size upfront, you see these kind of cost reductions with the power electronic based solution. But if you want to install this out over time in 2 phases or 4 phases over a 10 or 20-year period as needs arise, the overall MPV of that, or life cycle cost of that solution, significantly is lower than if you go and try and build an upfront solution on day one. So what it's really saying is you can initially invest for kind of known needs, short-term, medium needs. You can add or remove these as things change in time. Again, because they can be delivered very, very fast, you can do that with kind of less than 1 year notice. And what it does is provides a no regrets kind of decision for utilities with a significantly lower lifetime cost. And utilities around the world are beginning to sort of embrace this idea. National Grid in the UK are installing 5 of these modular power flow controllers on their grids this year, in the 275 and 400 kV grids. And these are releasing about 1.5 gigawatts of network capacity. And National Grid's system is such that, you know, you've got high wind generation in the north of Scotland, and you're trying to squeeze it down through the network to the load centers in the south. And they're being able to optimize this with power flow controllers, and these are kind of optimized pre and post contingency to support those increased transfers. From a cost perspective, that solution saved National Grid around up to 400 million when compared with new circuits or PSTs. So the benefits can be delivered very, very quickly and also at much lower cost. Transgrid in Australia, another example of a company that's using this modular power flow control technology, just south of the very, very south of New South Wales on the Victoria border. There's a large kind of hydro dam connected, and load centers in Sydney. They're trying to squeeze that power up through a constrained network. And optimally placing modular power flow controllers can release capacity in day one. In this case, about 80 megawatts of capacity, and they can scale that up before 2023 to between 180 and 220 megawatts on that particular corridor. So again, it's this idea of being able to kind of solve a need today, but also giving the utility the option to scale that up in the future. But power flow control you can also implement these or impact your distribution planning business. And I've shown here kind of just some areas that you can use these to help kind of implement or interconnect customers, implement some of your strategic objectives. And today I'll sort of focus on a couple of these. The first one is just improving voltage profiles for radial generators or loads. You can use flow controllers to, again, obviate or negate the need to build new infrastructure. And also just in terms of being able to close up kind of what are normally open points on distribution networks, you can do this and use flow control to manage thermal power flows and connect more distributed generation on the distribution network. I have some other kind of areas shown here as well where they can help provide benefits, but I'll focus maybe on the first two today. So this is a project actually in Canada where a utility is looking to increase, a cogeneration facility is looking to reduce its generation and import more power from the grid on a 25 kV circuit. Now, this is a long radial feeder, 28 kilometers in length, and the alternatives in this case to facilitating the customer's request is to build a new circuit or install a series compensation solution. So the utility is looking to kind of pull more power using a modular fax-based solution in this instance, and the benefits really of it over a traditional series capacitor A couple of them that kind of spring to mind are that there's negligible subsynchronous resonance issues. In this case, with a fax-based power flow controller versus a series cap, and it also just gives them greater flexibility in terms of siting and resiliency. So, with modular solutions, you no single point of failure. If a device fails, you don't lose your entire solution, which is, again, very different from traditional series capacitors, series reactors, or phase shifters. But it's just a typical example that I think in Alberta and in Canada more generally, a lot of these cogeneration facilities, mining loads are located at the end of radial feeders, and a power flow control solution can help to facilitate requests for increased or decreased demand. On the second kind of application I'll talk about on distribution networks is really around optimizing the network and closing up normally open points. So this is just an example of a typical distribution network where you've got between bus A and bus 1, you've got large electric vehicle demand connected, and on the flip side, on bus B and bus 2, you've got large generation connected, and being able to close up these two areas have to kind of optimize the overall network rather than kind of having to build new infrastructure. So if you look at the load profile on the left-hand side, at bus 1 in the middle of the night, we've got large load, electric vehicles are drawing down a lot of power from the grid and, in fact, overloading the circuit between bus A and bus 1. By closing up the normally open point, you can actually feed this load through two buses rather than one, and use power flow control to make sure that those thermal limits are maintained on all circuits. And so you're bringing your what was your kind of overloaded thermal loading on that line to back down to within the line rating. On the flip side, you've got a lot of generation connected at bus B or bus 2, and at high solar output, high peak output times of the day, you're pushing a lot of power up towards the transmission system and overloading that circuit. Again, a solution that might be looked at would be to reconductor or build a new circuit between bus 2 and bus B. But by closing up the normally open point, you can flow more power through onto bus 1 and out through bus A. So you're just kind of maximizing the use of your network with power flow controllers. These are just very simple examples, but help to illustrate the kind of benefits that flow control can have over traditional reinforcement solutions. And finally, just on the generation side of things, so how can kind of it impact really your generation or your demand customers? Well, the fact that they can be delivered, these types of solutions can be delivered within a year to maximize capacity means that you can allow wind farms, solar farms connect faster and potentially cheaper than traditional alternative solutions. You can increase transfer capacity for generators connected on the system today. So if you've got a wind farm connected, you can scale that wind farm up with kind of a modular flow control system or solution on the system. And any plant that's constrained today on the system, again, because of the fast delivery time, you can come in and relieve some of these system constraints for existing plants connected on the system. And UK Power Networks is an example of a distribution customer actually in the UK that's using this modular flow controller optimized across two different circuits to balance out power flows in real time to basically allow unconstrained generation export on their distribution network. So in this case, UKPN was looking at building new circuits, looking at reconductoring new circuits to facilitate new generation demand requests that they were receiving. But by using flow control across a couple of circuits, they were able to balance out the flows and allow an additional 95 megawatts of capacity to be released. Again, the solution just saved them around £8 million versus traditional alternatives. And this is kind of the future. This is optimized flow control, which is, reading line flows in real time. It's reading outputs of generators in real time, and it's actively dispatching different devices to correspond to that. So this is a kind of a way in which, an example of which they can help with on the generation side, and the same would apply for demand. So I think my time is probably up, but just really how can it be applied in Alberta? A lot of this, I hope, is resonating with folks in Alberta. It's a viable network. Power flow control is a viable network reinforcement option, and can help maximize utilization of already built transmission distribution networks. Recent advancements towards more modular forms of power flow control can really help lower investment capital and risk for utilities. And even can be installed as interim solutions to longer term new line or new reconductor projects. Flow controllers can help manage uncertainty with future res and uncertain load demand. So where justification of investments becomes difficult, I think a modular flow controller can help manage that and get you through kind of 5 to 10 years until you build out bigger solutions. And finally, then they can be used on the interconnection side of things as well. It can be used to help connect new generation or demand customers where capacity may be constrained. So that's kind of my presentation. If you have any questions, I'll probably deal with them at the end, but I'll pass back maybe to Ed to hand over to Marc.
Great. Thanks a lot, Brendan. Yeah, so Marc's going to give his talk now. Go ahead, Marc. Let you set that up on the PowerPoint.
Hopefully, you're seeing. Ah,
there it is.
All right, how's that looking?
Looks great.
So thank you everyone for joining. It's the idea to organize this webinar actually came about just as everyone else has probably been suffering to a certain extent with cancellation of conferences and these opportunities to get together in our industry and kind of discuss some of the things that are going on. And Alberta's really interesting context. There's a lot of really interesting stuff going on with regards to past developments, future developments of the system and where things are going with the future. So I'm going to take a somewhat different tack. I'm talking than Brendan. So I'm going to be talking a lot about the similar things, but I'm not presenting an actual solution. I'm kind of asking questions a little bit more about what the future is going to look like as we take on more and more levels of renewable energy, so the intermittency component, right? But I'm going to be looking at it in a somewhat different context than most people are generally used to thinking about it. So I'll start off by, I'm basically going to be talking about voltage, not frequency. So I'll just quick crash course in reactive power, what it is, the unloved member of the power community. And talk about traditional voltage control, how systems are kind of managed, voltage is managed now, why. Talking about a notion of a more active voltage control, right? Talk a little bit about TASMANIA, where they've been actually doing this since the early 2000s, and looking at some of the similarities, and it's an interesting way of maybe looking at what could be in the future for Alberta. And then talking about what does a potential voltage control scheme look like in Alberta, but at a very high level. So just get some terms out of the way, right? So what are we talking about when we talk about voltage management, right? There's basically 3 major areas, right? One is the notion of stability, and this is what most people are most familiar with, right? So what we're talking about is, contingencies. It's recovering from bad things happening on the network, right? Where you're outside of your normal operating range. Voltage regulation, different thing. Voltage regulation is about, is more a consequence of flows. It's about how your voltage varies across different elements of your networks, right? So we're talking about, the internal regulation of through a generator's impedance, then through the network regulation. It's effectively an application of Ohm's law, right? Voltage drop. But and then there's voltage control. So voltage control is not about contingencies. It's not about recovering. It's about driving the network. It's about how you control it. This is what the operators of our power systems do, right? They're the ones who are controlling the voltage. And that's what I'm going to be talking about today. So I'm not really going to be going into contingencies or regulation other than just as something that control has to deal with. And there's something that I really want to make a point here, is that voltage management is not really about managing voltage per se. It's actually about managing reactive power. And one of the things that, you know, we kind of know here is that, you know, if you sit back and you really think about it, voltage is actually not a good indicator of whether or not you're in a secure operating state, okay? Voltage is an outcome. If there is a reactive power shortfall, okay, and you have voltage issues, that's a stability problem. That is definitely an issue there. But if you've got plenty of reactive power and you've got voltage issues, it's actually a control issue. So it's not about stability. It's not about is there the reactive power out there. It's about, are you setting yourself up to be able to access the reactive power where it is? So just key concepts, right? So what is reactive power? It's that thing that we hear. It's actually, and what you hear is at 120 hertz, right? It's the exchange of energy between the electric and the magnetic fields, right? And that's why we say that it doesn't actually produce work, or that it's not real power, is that it's just energy exchange. It doesn't get used. It's being exchanged in the system, and it's provided by the generators, right? And so as we all know, there's the sinks for reactive powers, right? So thinking reactors and coils and stuff. But importantly, transmission lines, funnily enough, are actually big sinks, right? You know, and we can see it over here, right? They react with the square of the current, right? The magnetic field absorbs this, and that's what we often call losses, reactive losses, right? Transmission lines are also sources, right? Just as capacitor banks are and all that, right? Because, you know, you put something at potential, at a voltage above something that's not at voltage, and guess what? You get a capacitor, right? And the relationship of the reactive power of the charge that comes out of the line is actually, really interestingly, you know, the change in reactive power is actually, again, this is a nonlinear relationship. It varies with the squared of the power. So these are really basic principles. If you saw my LinkedIn post, I told you that I was going to show you some basic formulas, and this is them. This is about as deep as I get into formulas, right? But there's the important thing I want you to remember here is that voltage and power have a non-linear relationship. And I'm going to keep hammering on about this, right? Because if you think back to university, there's some special characteristics about linearizing around non-linear problems, right? So as I said, intermittency, now what I want to talk about is really beyond the supply balance issue, right? You know, we know that, you know, the system voltage is managed in a way that has worked for a really long time, right? You know, and it was designed, you know, as we developed our networks in the early, you know, from the 50s to the 80s, as we grew big networks. It was all about managing a predictable load ramp, and I'll talk about this a bit later. So I'll kind of jump on from the slide, right? That wherever, you know, as you know, Brendan was saying, there's some very similar impacts here with, you know, that occur with flows, is that when you're moving away from the way of operating the system that it was actually initially designed for, okay, you start having to manage things quite differently, and the exercise becomes to optimize the existing resources, right? So what we know is an intermittent does change voltage. It does do all sorts of stuff. You know, there's plenty of evidence of, you know, tap banks being switched way more, tap changers going, and you know, operators having to more and more manually intervene in the system. And the conclusion is, it's, again, back to what is controlled. The grid is becoming harder to control, okay? And this is due to intermittency, and it's just gonna get bigger and bigger as an issue, right? So what is traditional voltage control, right? It's the centrally planned system that was optimized, and it's basically all about following the load, right? And so you take this characteristic here, basically you've got generators that control locally. That little blue line there is where the voltage source is. You know, this is, by the way, these are visual diagrams. These are not simulations. These are conceptual, right? So, you know, you've got a generator controlling its local bus relatively solidly, and it's controlling that, and as the flow increases in the morning and the system ramps up, you start to get the regulation effect coming in, and you get the voltage that starts to sag. And then all of a sudden there's your nonlinear relationship going down as voltage decreases, and boom, here's where you're fixing for your linearization. You've got these discrete actions that are things like your cap bank switching, your online tap changers, compensating for load. So you have these discrete actions that allow you to move back to your linearization point effectively around your linear control, okay? And you can see right there, your reactive output kind of increases linearly. But the point, this gray box there, this is your generator's capability, right? And so the point I'm trying to make here is, a lot of the time there's a lot more capability out there. This is about what is the difference between low voltage due to control versus low voltage due to lack of reactive power, which is the bad bit, right? So I'm kind of going here on the basis that there's actually a lot more reactive power available than what we tend to think about, okay? So the cascading regulation zones, again, designed that way. Everything is about a load following system, okay? So what does intermittency do? Well, if you look up the definition of intermittency, it's random. That's what it is. It's a stochastic element that you start adding into your system. Now, when you've got a linear solution to a nonlinear problem, it's all about the assumptions that you put in. It's like, if you think back, it's where are you linearizing? And it works as long as you're operating around that point, right? But all of a sudden, what the randomness of intermittency does is that, guess what? Sometimes voltage is no longer load following. Okay, sometimes it's the reactive line loading that's determining the voltage, and that's a factor of flow, a factor of randomness, all right? And like I say, we know that this is happening, okay? Tap changers and equipment like that that's effectively designed to be load following is now becoming generator following and is responding to intermittency and effectively not operating the way that we want it. Control rooms everywhere are reporting it. They're having to call up, they're having to access reactive power on the fly when some operating outcome that, when you think about it from a market perspective is quite reasonable, just wasn't actually one that they're used to seeing, right? And then they got to work through it on the fly. So basically what we're saying now is that, the risk as this goes forward and as it continues is around putting in more and more network side solutions, okay, to generate more reactive power. When I'm hypothesizing, okay, there's a lot of reactive power available if you only capture it and use it, all right? So what I'm talking about here is basically active voltage control for the system, okay? It's basically AGC, okay, for reactive power. What you do is, so if you look on the two fancy diagrams, they're a bit busy there, but if you look on the top section there, what you're seeing is on the left-hand side is the traditional voltage control, basically, that I kind of just represented there, where what you see is that regulation characteristic going down when all of a sudden you get limited here because your reactive power, so your voltage, your N-1 voltage, if you will, is actually starting to exit that regulatory, like your limits, your 0.9 to 1.1 per unit kind of thing. And you end up with this issue and you've got this reactive power shortfall, apparent reactive power shortfall. But the question is that if that's not actually a reactive power shortfall, is the limitation just because you ran out of delta V, okay? You ran out of voltage headroom to deal with the contingency, but you'd recover just fine. I mean, the system, like 0.8 from the system perspective can be a very healthy voltage. It's your equipment that gets broken. It's people connected to the system that don't like it, right? So what I'm talking about now is actually going towards utilizing the full range, okay, of the delta V, that going and trying to figure out a way to actually do that. And so kind of using that using the nonlinear characteristic and implementing it as a control, which on your sending side, so where you're controlling, you actually inject that nonlinearity to get a linear behavior of the voltage at the receiving end when the trigger for voltage variation is not load. And this is the key, right? Because what we're trying to do is we're trying to keep the voltage set up in a way that your online tap changers and your cap banks are still there for you. Okay, they're there for you when you need to control the system, when your system is ramping up and down in the morning and up in the morning and down in the evening and doing all that kind of thing. That's what you're trying to keep them there for that. Okay, so what I'm trying to show here is that by going then from a linear increase of Q, so you got straight voltage, linear increase of Q here at the bottom of the output of the generator or of the source, right? Instead of going there is have a nonlinear V, which then results in a nonlinear reactive power output. And now what you're doing is you're actually lifting up you've basically eliminated your reactive power shortfall and you've freed up your ability to run more power across that system more dynamically. And all you've really done is you've given yourself the voltage headroom. You've built the regulation characteristic into your voltage control scheme, okay? So why is this hard? Like what's like, this sounds really easy, right? But what's the big deal about this? Why is this hard? Well, let's get back to legacy issues here about how the systems were planned and initially planned, right? Our planning processes, okay, we've got like 60, maybe 70 years of baked in thinking, baked in processes, baked in thinking, and everything's about reliability. And I'm not saying reliability is like, don't get me wrong here, I'm not saying we back out on reliability. What I'm saying is we need to start thinking about more than reliability, right? Are we creating extra reliability by effectively limiting the ability of reactive power to come out, right? So the result of that is that all of our simulation tools, okay, all of our criteria, they're all about analyzing a current moment in time, okay? We're not looking at there's not a lot of availability of tools out there to actually help us drive the network, right? And the classic, and you know, and I've been on both sides of planning. I've been in network planning and I've been in operations planning, and the classic thing is always the operational planners are telling the network planners, what's this thing that you delivered? I can't operate this. And then the transmission planner is saying, what are you talking about? We left you this great big wonderful asset that for you to manage. And it's that constant sort of tug of war between the two, right? So the way we're at now is that all of this works on predictability. It works when it works because what you've got is this regulating the cascading regulation that looks after the voltage kind of like by itself, okay? So what you're interested in is in each one of those specific instances in times, okay? Are you safe? Are you reliable? Are you secure, right? But there's not a lot of consideration about how do you get from one extreme operating state to another operating state. And then you end up with all sorts of weird things like ramp rate controls and things, right? So the result is that I believe, and this is not the hard thing to demonstrate, but around, and this is not an Alberta specific thing, this is an industry thing. There's an awful lot of N-1 voltage reliability reinforcement that is actually about delta V, not reactive power shortfall. Okay, so that's a big statement, and I'm expecting people to push back on that, but that's the conversation that I'm trying to stimulate here. So who's doing it? Tasmania. This is Australia. That little thing in the bottom there, that little island is Tasmania. I lived there for 4 years. The Watsons are from there. 500,000 people connected to the national electricity market via BASLink, which is an undersea HVDC cable. It's actually the exact same Siemens technology as the 2 HVDC links in Alberta. Connected a 220 kV bulk system. So this is a really little system, right? It peaks at about 1,800 megawatts of internal load, but they effectively added 600 megawatts of export capability on an 1,800 megawatt system. That's a 33% increase. I just did that in my head, without any network reinforcement. Okay, no network reinforcement. So what does that mean? What that means is that when you're at high load and then BASLink's pushing out, okay, you're in that weird part of the regulation curve. Okay, which means that like we were seeing cases when BASLink went first live that like 50 megawatts could do like a 6 or 7% voltage variation, and so there were ramp rate limitations on BASLink, and BASLink was not able to pursue prices because of the inability of the Tasmanian transmission network to control the voltage. There was plenty of reactive power there. It's just that we were operating in a certain part of we were out of the linearization zone, right, of how the system works. So what they've done, okay, is, so here's what the Tasmanian system kind of looks like, okay? So you've got this 220 kV triangle in the middle. You've got a load center down in the south, okay, which is Hobart. You got a smaller load center up in the north, central north, which is the city of Launceston. Your hydro generation in those big blue lines, or your remote generation that are coming in, that's your traditional, that was the system that was centrally planned and regulating, cascading regulation. And there's your HVDC link right in the top, plugging right into the most heavily loaded part of the system, right? The bit that's trying to get your power out of the northwest and down into Hobart. All of a sudden, you start seeing all this variation across the system. Those big green dots, okay, so Tasmania is located in the roaring 40s and the trade winds. It is a beautiful wind resource there. It's constant, it's there all the time, but it's also gusty, right? So it's not always, it's constant in its average, okay, but it's very, very gusty in its actual deployment, right? So what that means is voltage is just all over the place. So what did they do? They basically, from around 2004, I was involved in the first generation of this, of the control about this, was put in, they now have 2 voltage control schemes, right? So there's they manage the northern system, all right, as you know, to basically where they control the voltage at Basslink and Launceston. It's effectively electrically very close, so very much the same voltage point, right? They control that voltage there by regulating the 220 kV, by controlling the 220 kV voltage to compensate for the regulation characteristic of these lines when they're really heavily loaded. And just so you know, they actually run these lines. They do dynamic line ratings with post-contingent tripping of generation behind the fault. So they actually run their lines to like 90% of their thermal capacity pre-contingent, right? So it's like these lines are loaded to the max, right? So they manage it in the north, right? And so they aggregate the northern generator setting and they do like a sort of a prorated contribution. And every 30 seconds they send out a voltage target, okay? And it runs an EMS, okay? It sits right next to the AGC, okay? It goes through, it uses existing SCADA and inter-control room communication protocol, and there's nothing magical and mystical about it from the deployment side. It's just a piece of software in the EMS. But it's a piece of software that took a lot of thinking and a lot of so they've been doing this for 20 years now, right? What does it look like at the local generation? You're basically just plugging in this 20-30 second control loop, okay, so that it's much slower than your internal controls, your AVRs, your governors. You're way out of those time frames, but it's faster than your online tap changers and your, maybe if you've automatic cap switching, right? So you're positioning it between those two, and you can basically just do it as a simple open loop with a lookup table, right? You know, you could just take a few data points of where your system's loaded, do a lookup table, change your QREF based on that. You want to do something a little bit fancier and closed loop. Well, you can take that VREF coming in. That can be sent directly from a control room. Okay, here's the system I want, or it can be a pulse up, pulse down. Now, the reality is that most of the time it's sending out the same signal, right? Every 30 seconds, it's not changing. Okay, but what it is doing is that the minute that it sees that, and literally when I say the minute, I mean literally within the minute of those wind variations, the voltage is automatically starting to self-correct. Okay, and the voltage, you know, so you've got where the power is suddenly coming from. The sending side is starting to come up, okay, to keep that receiving end where it needs to be so that it's got the post-contingent delta V, right?
Mark, I'm just gonna interrupt for a second. So everybody, if you have any questions, please send those in right away by text, and I'm sure Mark will just be finishing up in the next couple. So
I'm gonna zip through. I'm known for this. My nickname as a kid was Motormouth, so sure.
Now we can answer the couple that we received, and other people that have their questions can hold up their hand and speak them verbally.
So I've just got a couple more slides and I'll just whip through it, because the thing is, the analysis hasn't been done for Alberta. I don't really know what a voltage control scheme would look like in Alberta, but I got some ideas, right? So if you look at Alberta right now, this is drawn from the AESO's latest 20-year plan, right? What we know is at Fort Mac, it's not a lot of variability coming out of there, right? These are mid-merit machines. Okay, they're generally, they are kind of the load following machine. You know, you kind of get a 600 megawatt out. There's not a lot of variability there. The variability comes about from that renewable generation in the south that's effectively displacing the price setter, right? Which is the coal generation east of Edmonton and in the central east, right? So what you've got there is this situation there where that's where you're actually having to, you know, that's where, and anecdotally, I'm hearing stories that yes, this is where it's saying, I have no evidence, I haven't seen it, but you hear the stories, right? So it's like, where are you going to be controlling, right? The obvious control point is going to be around sort of Calgary and Edmonton. And what you're doing is you're managing these flows sort of on a cut set that looks kind of like this, right? It's like you're measuring these major flows ins and out, and that's where you're going to be doing. That's where it would look, right? Keys to success, TAS Networks has told us, right? They know what it is, right? They know that you don't do this half, you don't just do it half. Like you go in, you go hard, and you've got to make it work, right? And you do it with all the right consideration. You have to work out all of your known outcomes. It's a lot of analysis, right? It's a lot of work. Documentation, control. You treat this like what it is, okay? This is a primary control system. Okay, what you're doing is you're actually taking the human out of the loop to be able to respond in the right thing. So AGC, I talked to one of the guys who wrote some of the first AGC code, and he tells me that this was exactly what it was like back in the 70s. Is people like, you can't take the operator out of the control loop. Well, guess what? It worked for AGC for real power. It can work for reactive power as well. But you need to develop the tools that are not there. You can do it with PSSE, but you need a lot of external control of the tool to be able to make it work. It's what I call sort of quasi semi-state simulation. You know, you need to identify all the operating conditions. You got to figure out who owns the scheme, who has got the right to go in and change it, what is the control protocol, who does it, what are the processes, what do you do when it fails? Okay, so we're talking like 2, 3, 4, 5 years, okay, minimum, before such a thing came in place. But the fact is that, do you really want to wait until it's too late, okay, to start looking at the problem? Because trust me, I'm not going to go into details, but you do not want to be Vermont, okay? You do not want to be the case where they've lost control of the system voltage, okay? Because intermittency has forced all of their regular generation off, and now they're just at the mercy of the sun and the wind, okay? It's not a good situation. So that was it. See, I wrapped that one up pretty quick. I did that in 23 minutes and 24 seconds, according to my timer. So that's actually a good record for me. I was only 15% over. There you go.
Excellent. Excellent. That's perfect. We do have a couple questions here. Just going to read them off here. So question for Marc's presentation, would this control scheme be applicable for both type 3 and type 4 wind turbines? Or would one work better than the other?
Yeah, so that's a great question, right? So basically, the way I answer it is the higher the number in your type, the better it works. Okay, so type 3s will work quite well actually, and look, in Tasmania they've even been able to get some of the original induction generators to work within this, and it's more of a very localized control around that. But type 3 and type 4 in particular, they're made to do this, right? They're not running, and they've got, you know, it's effective. Look, type 4, you're sitting there with this like great big old voltage source converter sitting there on the end of your network, right? These things are one of the most underutilized assets on our networks. Okay, I've been talking to wind farm operators across the country and all through the US, and asking the same question for the last couple of years. So do you guys ever track your reactive power output? How close do you ever get to, you know, coming to anywhere near the limit that you would need for reactive margin? And the answer is like, never. Oh, that's an interesting thing. That's an interesting statement. What's going on in your network? Oh man, they're spending lots of money on SVCs and cap banks and this and that, and it's just coming in everywhere. I don't know what's going on. It looks like we're causing all these stability issues. So yes, in answer to the question, yes, type 3 and type 4 machines are perfect for this. And the fact is, if you start thinking about it, if you wanted to take like a cause or pays approach, right? Who's creating the problem? Well, it's the intermittent one. You can fix it. You can actually fix it on the fly while you're doing it, right? And that's the beauty of it. That's the beauty of a responsive primary control system, right? That works like this, is that you're creating that space. I hope that was an answer to your question.
Great. Yeah, thank you, Marc. Brendan, we have a question for you. I have a question for SmartWire. When changing impedance of the line to control flow, would that also change, in brackets, lower the voltage of the line at the receiving end?
Yeah, that's a good question, and you're right. If you're increasing the impedance of a circuit, then you're lowering the voltage across that line. But on the flip side, if you series compensate a line, you lower the reactance of the circuit, you're actually boosting the voltage in a particular area of the network. So we've had, I know with SmartWires, we've had a number of applications where we're series compensating circuits to boost the voltage. So not for thermal power flow control reasons, but for actual voltage control. And again, as kind of Marc mentioned, these are voltage source converter technology, so they can be actively used to control voltage or power or current in real time. So it would depend on the application, but I would say that you would first kind of look at what impact you can do to lower thermal limits, and then check the voltage limits after that.
Okay, another question for you, Brendan. As a general rule of thumb, how much transfer capacity increase could be expected on the transmission circuit? 5 to 10%, 10 to 20% or more? And what's the best increase your solution has been able to unlock?
So good question again as well. And really, when it comes down to modular, because the devices or solutions are modular, if you want to increase alleviate a 10% constraint on a line, you install a certain number of modules to alleviate that constraint. But if you need to alleviate 50%, you just add more modules to it. So in theory, there's no limit to the actual constraint that you can relieve. From a kind of a thermal capability perspective, when your series compensating circuits up to 70-80%, that's when you start to see impacts on protection and voltage. But from our perspective, we kind of relieved anywhere from 10% to 190-200% kind of overloads on circuits. So really, there's no limit on how much of a constraint relief you can provide with flow control.
Okay, and Mark, coming back to you, if a utility was interested in voltage control in Alberta, what would you say is the next step?
Yeah, so the next step is basically you need to stop and think about it, right? So this is effectively an offline type of exercise where you need to, well, the first thing is you got to build your tools, right? You actually need to be able, so for instance, you could use PSSE, right, to do this quite effectively, but you need some pretty hardcore Python scripting to be able to do this quasi semi-state type thing, right? Which kind of looks like this. Is what you do is you start with your starting load flow, right? So you've got one generator topology, and then you want to then go and you want to inject in there a new generator topology, but you want to make sure you're locking out all your taps. You want to make sure that you're locking out all of your cap banks so that your primary voltage control, and then you start tweaking and you send the signals into your load flow. Now you're going to use this reference point, and now you're going to use this reference point, and then you just experiment with it, and you start working out that sensitivity of your system under the different conditions, right? And start building that, and then you start just looking at what is this like, where's the maximum like range? What are the operating conditions that we could possibly envision? And once you've got these tools that start working, right, then you just start running a lot of simulations, okay? A heck of a lot of simulations to through this quasi semi-state approach where you're doing different things. On the one hand, in these, say you could represent every simulation as a 5-minute step, and two things are happening. You can inject randomness into the over that 5-minute period, randomness into your generation profile, but also at the same time, if it happens to be during a morning ramp, what happens if onto my voltage when I've got a ramp of the load coming up on the one side and maybe wind coming down, you're ramping down or whatever that situation is, and starting to work on that and start to derive what your control parameters are. So that's the first sort of step, is getting a feel for it. And this is where you talk to your operator. Your operators, network operators, is like the source of all wisdom, right? And in terms of you want to get a reaction somewhere on the system, where do you need to go and do that to it, right? And your operators are the ones. So this is very much an operational planning issue, because that's what you're really doing. You're not talking about future assets here. You're talking about managing current assets. And so your operational planning group, you get in there, talk to the operators, get them to define these scenarios for you as a starting space, because they know. I'm sure they all know.
Great. Well, I just want to thank Brendan and Mark again for the excellent presentations, and you can look forward to getting the slides in your email. And thanks for attending.
And feel free to reach out to me directly. You saw my email; it'll be in the presentation. Any questions? I love talking about this stuff. This is why I'm in this industry, is thinking about stuff like this.
Great. Thank you.
Thank you, everyone.
Cheers. Thank you.